Just like we did with ethane carbon-carbon bond rotation, we are going to look at the energy considerations during a butane 360 rotation as well. So hopefully you recall from the last video that we ended up with 7 different conformations altogether. We started with this eclipsed conformation. We went to a staggered conformation that we're calling 2, another eclipsed conformation, staggered conformation, eclipse conformation, staggered conformation, and then finally number 7, which is actually redundant with number 1, but that gets us all the way back around in a 360 rotation to give another eclipse conformation. So here are the 4 eclipse conformations that we have so far. We have an angle of 0 degrees between the 2 methyl groups. We have a 120, we have the 240, and we have the 360 dihedral angles. With the staggered conformations, we have a 60-degree dihedral angle between the 2 methyls. We have a 180, and then we have the 300-degree dihedral angle. And maybe you've picked up on some similarities and differences between the different eclipse conformations. Notice that here, if we had to name the eclipsings that were taking place, we would say that there is a CH3 eclipsing, and then we have an HH eclipsing and an HH eclipsing here. On this eclipse structure, we have a CH3H eclipsing, another CH3H eclipsing, and an HH eclipsing interaction. Here we have a CH3H eclipsing, an HH eclipsing, and a CH3H eclipsing interaction. And then finally, we're back to a CH3 eclipsing, an HH eclipsing, and another HH eclipsing interaction here. As far as the staggered conformations go, notice that in 2 of the 3, you have a separation of the 2 methyl groups by 60 degrees, either in the, we could call this the minus 60 degree or the plus 60 degrees, but there's the same angle there between those 2 methyl groups. And then here, this one is different because there's a 180 degree dihedral angle between the 2 methyl groups. It turns out that not all eclipsing interactions are equivalent. So we learned in the last exercise with ethane that an HH eclipsing interaction costs approximately 4 kJs per mole. And what we discussed about that was that it meant that for every one of those interactions, the molecule would need that much energy to be able to actually undergo that interaction for the rotation to take place. And so you can see that that's occurring 2 times in this particular eclipse structure. But then you have methyl-methyl eclipsing up here, and this is a bit more costly. This methyl-methyl eclipsing interaction is 11 kilojoules per mole, so more than twice as much in terms of energy cost than an HH eclipsing interaction. And so then you have another 2 of those going on here, just like in structure 1. And so all together, if we have 4 kJs, and 11 kJs, so that's 11 plus 8, or these are about 19 kJs per mole in terms of rotational energy. That's how much it would cost to be able to have to go through that particular conformation. Down here with structures 3 and 5, it's a little different. You have 1 HH eclipsing, that's 4 kJs per mole. But then up here you have a CH3H eclipsing, and that one turns out to be 6 kilojoules per mole. So it's a little higher. You have another one here, another 6 kJs per mole. So this would be a 6 plus 6 plus 4, or a 12 plus 4. So this would be about a 16 kJ per mole cost. Same thing, excuse me, for number 5, where you have CH3H So this is a 6. You have CH3H. So this is a 6. And then you have the HH, which is a 4. So once again, we are left with about 16 kilojoules per mole for this particular conformation. So we learned about something called torsional strain when we were looking at ethane, and we saw that, well, these two eclipsing one another, the reason that you had to have 4 kilojoules per mole for that interaction to be even able to take place is that the sigma electrons that are here and here are going to repel one another, right? So you have this sigma electron-electron repulsion. And you have that again, of course, going on in the back, right? And so that was torsional strain. You still have torsional strain taking place here and here. So you still have sigma electron-electron repulsion. But in addition to that, when you have the methyl groups present, you have a new kind of strain that's taking place. So if you think about each of these methyl groups, they have a cloud, so to speak, of electrons around them, right? There's a lot of electron density surrounding these groups, and so that's kind of what I'm trying to show here in blue. And you can see how these are going to get in each other's way. This type of strain is a new type of strain, and it is called steric strain. And it's for that reason that with the methyl-methyl eclipsing, you not only have torsional, but you have steric strain as well. And so it jumps all the way up to 11 kilojoules per mole per methyl-methyl eclipsing interaction. And so this is a second type of strain that is present when you have anything that's larger than a hydrogen atom. You now have to consider not just torsional strain, but also steric strain. Now let's take a look at the staggered conformations. And we discussed the fact that 2 of these had the same angle essentially between the 2 methyl groups, and then this one was by itself at 180. Even though the methyl groups here are not eclipsing one another, just the fact that they're getting close to one another, you start to have some of this steric strain. Now, you're not going to have the torsional strain, and it's not going to bump it all the way up to 11 kilojoules per mole, but what you do have is about a 3.8 kilojoule per mole interaction there. And this particular interaction, when the methyl groups are at a dihedral angle of 60 to one another, is called a gauche interaction. G-A-U-C-H-E, a gauche interaction. Down here, you have the methyl groups as far apart from one another as they can get. There is no torsional strain. There's no steric strain taking place. And so this conformation is going to be the lowest energy conformation. And this conformation is called the anti-conformation. And so within the staggered conformations, we have 2 what we call gauche conformations and 1 anti-conformation. So once again, here's a look at that gauche interaction that you have taking place that costs 3.8 kJs per mole. And that's due to a steric repulsion between the 2 methyl groups. So if we want to create an energy profile like we did for the carbon-carbon bond rotation of ethane, we can do the same thing with butane with respect to the C2-C3 bond rotation and taking a look at the CH3-CH3 dihedral angle. And at the top of the energy hill, so to speak, would be conformations 1 and 7, where you have the costly CH3 eclipsing interactions that are taking place. So that would be the energy, those would be the energy maxima. The minimum would be structure 4, where you have the anti-conformation, the 180-degree dihedral angle between the two methyl groups, where you have minimum steric and torsional strain. Just below the CH3 eclipsed, you have the other two eclipsed conformations, where you have CH3H eclipsings taking place, as well as HH eclipsings, of course. And then finally, you have the other staggered conformations that we call gauche, and these are going to be slightly higher in energy than the anti-staggered conformation. If we were to generate a curve going through this 360-degree rotation, it would look like this. And the energy gap between the high energy CH3 eclipse conformation and the low energy anti-conformation would be 19 kilojoules per mole. The gap between the slightly lower energy eclipse conformation and the anti-conformation would be 16 kilojoules per mole. And then finally, the gap between the so-called gauche staggered conformations and the anti-conformation is 3.8 kJs per mole. So if you're having trouble following where those numbers came from, I suggest that you go back to the slides where we discussed, you were given the values for the different types of interactions, and see if you can convince yourself that these are indeed the energy gaps there. The numbers are also summarized in the soft chalk module for this video.